10 billion years of darkness ended last July. It arrived at 61 kilometers per second, cut inside the orbit of Mars, and disappeared forever. On the 1st of July 2025, a telescope in Chile confirmed it had come from outside our solar system. It was the third interstellar visitor ever confirmed. It was the largest of them all, by far. And it was carrying chemistry that has never been seen in any comet. For a decade, no one knew what ice from another star system would look like up close. Then the James Webb Space Telescope measured the ice inside its coma. It had formed 10 billion years ago, before the Sun existed. We will trace its origins, read its chemistry, and follow it into the deep past. Subscribe if you want the full picture. It was the oldest object ever measured. This is what it told us. Every object in our solar system is, in the most fundamental sense, a prisoner. The planets, the asteroids, the comets, everything is held in place by the Sun's gravity, locked into orbits that curve back on themselves and repeat forever. An object that arrives in our neighborhood from outside that system does not follow those rules. Its path does not curve back. It arrives, cuts through, and continues outward without ever returning. In the language of orbital mechanics, this is called a hyperbolic trajectory, and there is a number that tells you how hyperbolic a path is, a measure of how sharply the orbit opens, how decisively the object breaks free. That number is called the eccentricity. A perfectly circular orbit has an eccentricity of 0. An orbit that forms an elongated ellipse, the kind most comets in our solar system follow, sits between 0 and 1. The moment the eccentricity exceeds 1, the object is unbound. It is passing through. When astronomers studied the trajectory of the object detected on the 1st of July 2025, the eccentricity they measured was 6.141. That is not slightly above the threshold. It is more than 6 times the minimum value that defines an unbound visitor, the highest eccentricity ever recorded for any object observed in our solar system. Nothing before it had measured this high. The object was moving at 61 kilometers per second relative to the Sun when discovered, already inside the orbit of Jupiter, at a distance of 4.5 astronomical units. Nothing we have ever thrown into interstellar space moves that fast. You cannot reach 61 kilometers per second by being flung out of a star system like ours. You carry that speed because your source population is ancient, because billions of years of gravitational scattering have accumulated in your velocity. The speed is not just a number, it is a signature of age. The telescope that first logged this object was not specifically hunting for interstellar visitors. The Asteroid Terrestrial Impact Last Alert System, a network of survey telescopes funded by NASA and operated at sites across the globe, including a station at Rio Hurtado in Chile, exists primarily to find asteroids that could threaten Earth. On the 1st of July 2025, the Chile station recorded a faint moving point of light and submitted the observation to the Minor Planet Center. Follow-up work over the next 24 hours confirmed something extraordinary. The trajectory was not merely eccentric, it was interstellar. Within hours of that confirmation, an amateur astronomer named Sam Dean was already working through archival data from earlier survey runs. Moving backward through images from the same telescope network, Dean pushed the pre-discovery record back to the 14th of June, 16 days before the official detection. The object had been crossing the sky the whole time, largely hidden by the misfortune of its path. It was traveling in front of the dense star fields near the galactic center, now a region so crowded with background light that automated detection systems had struggled to distinguish a moving point source from the noise behind it. This was the third such object humanity had ever confirmed. The first, discovered in 2017, was 1I Oumuamua, an asteroid-like body with no detectable coma, an extreme elongated shape, and a behavior so strange that scientists spent years producing competing hypotheses about what it could possibly be. The second, 2I Borisov, arrived in 2019 with a visible coma and a tail, behaving far more like a conventional comet in its chemistry and structure. The two objects could hardly have been more different from each other. David Jewett, who led the observational effort on both, noted that the only property they clearly shared was where they had come from. Outside this solar system was the full extent of the shared biography. The third was different again, and in almost every measurable dimension, it was larger. Here is something worth sitting with for a moment. Our solar system did not hold on to its own planetesimals. During the period of giant planet formation, as Jupiter and Saturn grew and their gravitational fields reached outward, they scattered an enormous fraction of the small icy bodies that had formed in the outer disk. The process was relentless. Each encounter between a planetesimal and a giant planet flung debris into new orbits, and most of those orbits ultimately led out of the solar system entirely. Every star system that has ever formed giant planets has almost certainly done the same. The astronomer Michelle Bannister put it this way: planets are like active correspondents, and they move trillions of small bodies out into galactic space. The galaxy is full of them, fragments of ancient worlds drifting in the dark for millions of years, for billions of years, waiting to cross another star's path. What arrived on the 1st of July 2025 had been traveling longer than the Earth has existed. The trajectory of an interstellar object tells two stories at once. The first is practical: where it came from, what it passed, and where it is going. The second is older and harder to read. Locked inside the geometry of the path are clues about the age of the source population, the kind of star the object once orbited, and how long it has been in motion. To extract those clues, you need one more number, not the eccentricity which describes the shape of the path, but a related quantity that describes the speed the object will carry long after it has left our sun behind. When any object falls toward the sun, it accelerates. As it climbs back outward, it decelerates. A comet from our own Oort cloud follows this pattern faithfully. It falls inward from a vast distance, races through the inner solar system at its fastest, then slows as it climbs back toward the cold outer dark. Follow it far enough from the sun, and its speed converges towards zero. It stays bound. An interstellar visitor does not. It arrives with a surplus, a velocity above and beyond what the sun's gravity contributes. Strip away the sun's gravitational influence entirely, and what remains is called the hyperbolic excess velocity, the speed the object carried here from its source, and the speed it will carry away into the dark. For 3I Atlas, that number was 58 kilometers per second. For 1I Oumuamua, it was 26. For 2I Borisov, 32. 3. I arrived more than twice as fast as either of its predecessors. That gap is not incidental. An object does not accumulate 58 kilometers per second of excess velocity by being recently ejected from a nearby young star. It accumulates that speed through billions of years of gravitational interactions, scattering encounters with stars, with molecular clouds, with the spiral arms of the galaxy itself. The velocity is time, written in motion. The three eccentricities now complete the picture. 1I Oumuamua, 1.2. 2I Borisov, 3.4. 3I Atlas, 6.141. Plot those paths and the progression is visible. 1. I's trajectory curves noticeably. The sun's gravity bends it into a clear arc. 2. I curves less. 3. I is nearly straight. An eccentricity of 6.141 describes a path so little deflected by the sun that it appears almost linear. The sun barely registers as an obstacle. The object was in too much of a hurry to be meaningfully turned. Now consider the orientation of that path. Most objects in our solar system, the planets, the asteroids, the short-period comets, orbit the sun in roughly the same plane and in roughly the same direction. This shared plane is called the ecliptic, and it reflects the geometry of the disk from which the solar system formed. 3I Atlas's trajectory was tilted 175 degrees relative to that plane. An inclination of 0 degrees would mean the object was moving with the planets. An inclination of 90 degrees would mean it was crossing their orbits at a right angle. 175 degrees means it was moving almost exactly in reverse. A retrograde orbit, nearly opposite to the flow of everything else in the solar system. The object approached from the south of the ecliptic plane, placing it in the southern sky where observatories in Chile and across the southern hemisphere had the best early view. It is one reason the Atlas Survey telescope in Chile caught it first. The full itinerary of its passage is worth setting out. A 3I Atlas entered the solar system from the direction of the constellation Sagittarius, the same crowded region of sky that hosts the galactic center. It reached its closest point to the Sun on the 29th of October 2025, passing just inside the orbit of Mars at 1.356 astronomical units from the Sun. It came closest to Earth on the 19th of December 2025, at a distance of 1.8 astronomical units, roughly 1 3/4 times the Earth-Sun distance. Close enough for intensive observation, but never any kind of threat. It then swept outward past Jupiter on the 16th of March 2026, coming within 0.358 astronomical units of the planet before continuing its passage toward the outer solar system and beyond. Darryl Seligman, who led the team that published the first formal orbital solution, and Davide Farnocchia at the Jet Propulsion Laboratory, whose navigation work then refined it, had confirmed the full picture within days of the discovery. Jane Liu, working with the Nordic Optical Telescope, confirmed within 48 hours that the object was actively outgassing, that it had a coma and was therefore a comet rather than a bare rock. The numbers were unambiguous. 3I Atlas was not simply passing through our neighborhood. It was already leaving, and it had things to show us before it did. A coma is not the comet itself. The nucleus, the actual solid body, and the frozen heart of the thing is typically a few kilometers across at most. What you see when you look at a comet in the sky is mostly not the nucleus. It is the cloud of gas and dust that the nucleus sheds as it warms, a vast, diffuse atmosphere called the coma, which can expand to diameters measured in tens of thousands of kilometers, sometimes hundreds of thousands. Trailing behind it, shaped by solar radiation and the solar wind, are the tails, a dust tail curving gently away from the sun, and an ion tail driven almost straight back by the pressure of the solar wind. 3I Atlas had all of this, and the scale of it was immediately striking. When Jane Liu and colleagues imaged the object with the Nordic Optical Telescope on the 2nd of July 2025, what they found was a clear, or diffuse appearance, a coma that was already active. By the time early high-resolution images were obtained with the Gran Telescopio Canarias, the coma measured approximately 26,400 kilometers in one direction and 24,700 kilometers in another. That is roughly twice the diameter of Earth. The nucleus producing all of that activity, the actual solid body doing the outgassing, was somewhere buried inside it, invisible behind its own exhalations. The distinction between an active comet and an inert asteroid matters more than it might seem. When 1I Oumuamua passed through in 2017, there was no coma at all. No outgassing was detected. It moved through the inner solar system in silence, a bare rock of unknown composition, giving almost nothing away. Scientists spent years arguing about it because the absence of activity meant the absence of measurable chemistry. 2I Borisov in 2019 was different. It outgassed, it had a coma and tails, and it could be studied as a conventional comet. 3I Atlas was like 2I in that sense. It was talking, and what it was saying was unusual from the very first observation. Here is something that carries more weight than it first appears. NASA's Transiting Exoplanet Survey satellite, known as TESS, had caught the object before anyone knew what it was. Processing of archival TESS data showed that 3I Atlas was already exhibiting cometary activity on the 7th of May 2025, when it was approximately 6.4 astronomical units from the Sun, roughly 6.5 times the Earth-Sun distance, well out beyond the orbit of Jupiter. The significance is chemical. Water ice does not sublimate efficiently at that distance. The temperatures are too cold for water to drive out gassing. For a comet to be active at 6.4 astronomical units, something more volatile than water has to be responsible, most likely carbon dioxide or carbon monoxide, both of which turn to gas at far lower temperatures. The object had been shedding material for months before any telescope on Earth had logged it. The color of the coma in its earliest observations was reddish, a spectral slope consistent with what astronomers call D-type asteroids, the darkest and most primitive class of small body in the outer solar system. And that redness is not paint, it is chemistry. It is the product of billions of years of bombardment by galactic cosmic rays, high-energy particles that stream through interstellar space and steadily alter the organic compounds in the surface ices of any body exposed to them long enough. The resulting material, called tholins, is dark, reddish, and complex. Finding it in the coma of 3I Atlas told observers that the surface ices of this object had been in open interstellar space for an enormous period of time. The color was a clock. The first optical spectroscopy, obtained in the days after discovery, added a further detail. Luis Salazar Manzano and collaborators, observing with telescopes at the MDM Observatory, found that 3I Atlas belonged to a category of comets classified as depleted in carbon chain molecules. Specifically, the ratio of diatomic carbon to cyanogen in its coma was far lower than in most solar system comets. In comets born in our own system, this kind of depletion is understood to be primordial, set in the parent disk at the time of formation, not acquired through later processing by sunlight. It is a fingerprint of where in a protoplanetary disk the body formed, and under what conditions. Finding it in 3I Atlas gave observers a chemical signature from another star system, confirmed before the James Webb Space Telescope had taken a single measurement. There was also something unusual in how the coma's dust scattered light. Tomas Santana Ross and Alexandra Ivanova, analyzing polarimetric measurements from the same early observation period, found an unusually strong negative polarization and an anomalously low inversion angle. For astronomers who study cometary dust, this pattern indicates particles that are large and compact, physically distinct from the sub-micron fluffy grains that dominate the coma of a typical solar system comet. The dust in 3I's coma was different in kind, not just in degree. When the Hubble Space Telescope took its first images on the 21st of July 2025, David Jewitt and his team saw all of this resolved into shape. The coma appeared as a teardrop, with a prominent fan of material extending toward the sun, a sunward plume, pointing into rather than away from the star. It was this plume, combined with the coma's asymmetric geometry, that told observers the activity was not uniform across the nucleus. Something specific on the surface was driving it. The object had structure, it had directionality, and none of its chemistry looked quite like anything that had been seen before. Every atom and molecule emits and absorbs light at specific wavelengths, a signature as individual as a fingerprint. When sunlight passes through the cloud of gas surrounding a comet's nucleus, each species of molecule leaves its mark on the spectrum, a pattern of absorption and emission lines at wavelengths unique to that compound. This is how astronomers read the chemistry of objects they can never touch. You aim a spectrograph at the coma, disperse the incoming light into its component wavelengths, and compare the resulting pattern against a library of known molecular signatures. In the infrared part of the spectrum, the range beyond what the human eye can detect, the signatures of water, carbon dioxide, carbon monoxide, and dozens of organic molecules are all accessible, each one a distinct fingerprint, each one readable if the telescope is sensitive enough. For nearby comets, ground-based telescopes have been doing this for decades. For a visitor moving as fast as 3I Atlas, the window of opportunity was narrow, and the instrument that mattered most was the James Webb Space Telescope. The near-infrared spectrograph on the James Webb Space Telescope is sensitive to wavelengths that water, carbon dioxide, and carbon monoxide all absorb and emit strongly, a range where the chemistry of comets is written most clearly. Martin Cordiner at NASA's Goddard Space Flight Center led the team that turned the telescope toward 3I Atlas on the 6th of August 2025, when the object was still inbound at 3.3 astronomical units from the Sun. What the spectrograph returned was not what anyone expected. The coma was dominated by carbon dioxide, not water, carbon dioxide. The mixing ratio of carbon dioxide to water in the coma was approximately 8:1. To understand what that means, consider that the vast majority of comets in our solar system carry far more water than any other volatile. Water is the dominant driver of cometary activity in the inner solar system, and the benchmark against which every other molecule is measured. A carbon dioxide to water ratio of 8:1 is not just unusual, it is among the highest ever recorded in any comet. The only solar system object with a comparably inverted ratio is a peculiar comet that is considered a genuine outlier and is still not fully understood. 3I Atlas was in that company from the very first spectrum. The production rate numbers make the scale of it concrete. In that August observation, the nucleus was releasing 129 kilograms of carbon dioxide every second. It was releasing 14 kilograms of carbon monoxide per second. It was releasing just 6.6 kilograms of water per second. Carbon dioxide was carrying more than 85% of the total gas output. Water, the molecule that defines cometary activity for every comet in our solar system, was a minor constituent. The puzzle this creates is significant. Why would a comet be so carbon dioxide rich? Two explanations have been seriously proposed. The first is that 3I Atlas formed beyond the carbon dioxide frost line in its parent protoplanetary disk, far enough from its star that carbon dioxide ice could condense and accumulate in large quantities, while water ice was less abundant or differently distributed. The second is that the nucleus has developed an insulating crust over its billions of years in interstellar space, a layer of processed material that suppresses water sublimation while allowing the more volatile carbon dioxide to escape. The observations alone cannot distinguish between these possibilities, but the isotopic measurements, which come later in this story, offer a powerful constraint. The spectrophotometer for the history of the universe, epoch of Rayonization, and ICES Explorer, known as Sphere X, provided independent confirmation of the carbon dioxide dominance in mid-August 2025. Carey Liss and collaborators found an extended carbon dioxide coma stretching hundreds of thousands of kilometers from the nucleus, well beyond what the James Webb Space Telescope had mapped in detail. The Sphere X data also detected water ice directly, not as a gas, but in absorption, fine grains suspended in the coma, too cold to be sublimating efficiently, but present nonetheless. The Atacama Large Millimeter Array's compact configuration contributed a different layer to the picture. NX Roth and collaborators mapped the spatial distribution of methanol and hydrogen cyanide in the coma. Both molecules were detected with distinct outgassing geometries, suggesting they were originating from different regions of the nucleus or being released by different mechanisms. The ratio of methanol to hydrogen cyanide in the outflow was unusually high by the standards of solar system comets. Both molecules belong to a class of organic compounds that chemistry considers prebiotic, molecular building blocks relevant to the processes that eventually gave rise to life. Their presence in the coma of an object from another star system does not constitute evidence of life. What it does demonstrate is that the same raw molecular ingredients form readily in protoplanetary disks across the galaxy, regardless of the stellar environment in which those disks existed. A tentative detection of carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur, rounded out the volatile inventory. It was the sulfur-bearing component of a chemical portrait that was already unusual by almost every measure. The volatiles told one kind of story, the metals told another. In 2021, Jean Mainfroy, Damien Hutzemeckers, and Emmanuel Jehin at the University of Liège published a result that surprised the comet science community. Iron and nickel vapor were present in the comas of solar system comets, detected even at large distances from the Sun. The two metals appeared in roughly equal proportions, a ratio broadly consistent with the cosmic abundance of these elements, and with what would be expected if a common rocky material were sublimating from the comet's surface. When 2I Borisov passed through, the same pattern held. Finding iron and nickel in a cometary coma had become, by the time 3I Atlas arrived, an established, if still somewhat mysterious, observation. 3I Atlas broke the pattern immediately. When Cyrielle Opitom and collaborators observed the comet with the Very Large Telescope in the weeks after discovery, the nickel-to-iron ratio in the coma was not approximately equal. It was vastly higher, far above the range seen in any solar system comet. Nickel was present at levels that iron simply did not match. The anomaly was extreme enough to be unmistakable. What happened next was more interesting than the anomaly itself. As 3I Atlas approached the Sun and temperatures in the coma rose, the ratio changed. It normalized. By the time the object was substantially warmer, and the nickel-to-iron ratio had converged toward values consistent with other comets classified as carbon chain depleted. The anomaly had been a function of temperature, and its evolution as the comet warmed pointed directly at a mechanism. Hutzemeckers and collaborators proposed an explanation. The temperature dependence of the ratio is consistent with two distinct organometallic compounds sublimating at different rates, nickel tetracarbonyl which is extremely volatile and requires very little heat to boil off, and iron pentacarbonyl, which requires more. At large distances from the Sun, where temperatures are low, the nickel-bearing compound dominates. Nickel is released abundantly, while the iron compound has barely begun to sublimate. As the object warms on approach, the iron compound contributes increasingly, and the ratio normalizes. This model explains not just the ratio itself, but the specific pattern of its evolution with heliocentric distance. It also carries an implication. Carbonyl compounds, volatile organometallic molecules, are present in the cometary material. These are not compounds commonly discussed in the context of solar system comets. Their presence added yet another layer to a chemical profile that was becoming genuinely novel. Earlier, in discussing the coma's spectral properties, we noted that 3I Atlas is classified as depleted in carbon chain molecules, that the ratio of diatomic carbon to cyanogen was far below the norm for solar system comets. Bain and Schleicher had established that this kind of depletion in solar system comets is primordial, not acquired through solar processing. It encodes conditions in the parent disk at formation. What the post-perihelion observations now showed was that this depletion was not uniform through the object's interior. After perihelion, as solar erosion stripped away the outer layers, the carbon chain depletion became less severe. The ratio of diatomic carbon to cyanogen recovered somewhat. Metal production rates increased substantially relative to the inbound measurements. These changes point toward a nucleus that is compositionally layered, with an outer region transformed by billions of years of cosmic ray irradiation and a deeper interior that is more chemically intact, progressively revealed as the Sun peeled back the surface during the closest approach. The comet was showing observers its inside for the first time in 10 billion years. The most striking post-perihelion finding came from the James Webb Space Telescope's mid-infrared instrument. Matthew Belyakoff and collaborators, observing in December 2025, reported the first detection of methane in any interstellar object. Methane is hypervolatile. It sublimates at temperatures far below those required by carbon dioxide or water. Its appearance in the coma after perihelion, at a time when water activity was declining, is consistent with methane ice, having been buried beneath less volatile compounds throughout the inbound journey. Only the intense solar erosion of perihelion had exposed the methane-rich interior to space. The final confirmation of the scale of 3I Atlas's atmospheric activity came from X-rays. In late November and early December 2025, two space-based X-ray observatories, Japan's X-ray Imaging and Spectroscopy mission and the European Space Agency's XMM Newton, observed 3I Atlas and found a diffuse X-ray glow surrounding the nucleus. This made 3I Atlas the first interstellar comet ever seen in X-ray light. The glow is produced by solar wind charge exchange. High-energy ions streaming outward from the Sun collide with neutral atoms and molecules in the cometary atmosphere, releasing X-ray photons as their energy is redistributed. The detection confirmed that the gas coma was dense and extensive enough to intercept solar wind ions at a measurable rate. The atmosphere of an object from another star system was interacting with the radiation environment of our Sun. Two systems in contact across 10 billion years for a few months, before the visitor moved on. Not all hydrogen is the same. The most common form of hydrogen, the one that makes up the vast majority of the element in the universe, has a nucleus consisting of a single proton. But there is a heavier variant, called deuterium, whose nucleus contains both a proton and a neutron. Deuterium is stable. It is not radioactive, and it participates in chemical reactions in ways that are subtly different from ordinary hydrogen, because the extra neutron changes the mass of the atom, and mass affects the rate at which chemical bonds form and break. In very cold environments, temperatures of a few tens of degrees above absolute zero, which is to say temperatures far below anything you encounter on Earth's surface, chemical reactions preferentially incorporate deuterium into molecules. Water molecules form with deuterium substituted for ordinary hydrogen. So do methane molecules and many others. The colder the environment in which these molecules form, the more efficiently this enrichment occurs. This means that measuring the ratio of deuterium to ordinary hydrogen in a molecule is, effectively, a thermometer, a record of the temperature of the environment in which that molecule was born. The ratio is set at formation and then preserved, sometimes for billions of years, in the ice of a comet nucleus. In March 2026, Martin Cordner and collaborators submitted a paper to the journal Nature reporting measurements of the deuterium to hydrogen ratio in the water vapor of 3I Atlas's coma, obtained with the James Webb Space Telescope in December 2025. The ratio they measured was 0.95%, with an uncertainty of plus or minus 0.06%. To put that number in context, the highest deuterium to hydrogen ratio ever measured in the water of any solar system comet is roughly 1/10 of that value. The water in 3I Atlas carries more than 10 times the deuterium enrichment of the most deuterium-rich solar system comet ever studied. For the water ice in this object to carry such a ratio, it must have formed at temperatures below 30 Kelvin, below minus 243 degrees Celsius, in a cold, dense, shielded environment where the fractionation chemistry could operate at maximum efficiency. These are conditions found in the midplane of a protostellar disk, deep inside the coldest regions of a molecular cloud, or both. The paper also reported the carbon-12 to carbon-13 ratios in both carbon dioxide and carbon monoxide. In our solar system and in nearby interstellar clouds, carbon-13 makes up roughly 1% of all carbon, a specific abundance set by the history of stellar nucleosynthesis in our galactic neighborhood. The carbon-12 to carbon-13 ratios in 3I Atlas's carbon dioxide and carbon monoxide both exceeded those values. They were elevated relative to solar system norms and relative to the local interstellar medium. This matters because the ratio of carbon-12 to carbon-13 in a given environment is set by how many generations of stars have lived and died in that environment. Stars produce carbon-13 through nuclear burning and release it into the interstellar medium when they die. An environment that has seen fewer generations of stellar enrichment has less carbon-13 relative to carbon-12. A ratio elevated above solar system values points toward an older, less chemically enriched environment, one that formed before the galaxy had been thoroughly seeded by successive generations of stellar death. A second paper, submitted to Nature Astronomy in March 2026 by NX Roth and collaborators, reported the deuterium to hydrogen ratio in the methane in 3I Atlas's coma. The value was 3.31%, with an uncertainty of plus or minus 0.34%. Comet 67P/Churyumov-Gerasimenko, the comet visited by the European Space Agency's Rosetta spacecraft, the most thoroughly studied comet in history, was measured in situ and found to have a methane deuterium to hydrogen ratio of approximately 0.24%. 3I Atlas's ratio is 14 times higher. This was only the second detection of deuterated methane in any comet ever made, and the first ever achieved by remote spectroscopy rather than a spacecraft flying through the coma. The measurement required the James Webb Space Telescope's sensitivity operating at the limits of what is currently technically possible. The combination of the two deuterium measurements, independently obtained, independently analyzed, in two chemically distinct molecules, is where the power of the result lies. Water and methane form by different chemical pathways and in different conditions. For both to carry extreme deuterium enrichment simultaneously, the entire molecular inventory of this object must have formed in an environment where the elemental deuterium to hydrogen ratio was itself very high. That kind of environment exists in cold, dense interstellar cloud cores and in the mid-planes of protostellar disks embedded in such clouds. It is the kind of environment that existed in the early galaxy, before hydrogen had been cycled through many generations of stellar processing. Both molecules are telling the same story. They formed in the same kind of place, at roughly the same kind of temperature, at roughly the same time. When these isotopic measurements are interpreted against models of how the carbon-12 to carbon-13 ratio in the interstellar medium has evolved over the lifetime of the galaxy, as each generation of stars forges and releases carbon-13, the conclusion is that 3I Atlas accreted its material roughly 10 to 12 billion years ago. Not 10 million years ago, not 1 billion years ago, 10 to 12 billion years ago. Cyrielle Opitom and collaborators, using the Very Large Telescope, added a third isotopic fingerprint. They measured the nitrogen-14 to nitrogen-15 ratio in the cyanogen in 3I Atlas's coma and found a value of 343. Solar system comets typically show values around 150. 3I Atlas's nitrogen ratio is more than twice as high. Three independent isotopic systems, hydrogen in water, hydrogen in methane, nitrogen in cyanogen, all pointing in the same direction, ancient, metal-poor, formed early in the history of the galaxy. The solar system is 4.6 billion years old. When 3I Atlas accreted around its parent star, our solar system did not yet exist. The question that remains is where in the galaxy that parent star was, and what the galaxy looked like when it burned. The Milky Way is not a uniform structure, it is layered. The most obvious component is the thin disk, a flat, gas-rich pancake roughly 1,000 light-years deep, where most of the galaxy's current star formation takes place. The Sun lives here, and so do most of the stars you can see on a clear night. But beneath and above the thin disk, extending to several times its thickness, is an older and more diffuse component called the thick disk. Its stars are not forming new. They formed long ago, and they carry the chemical signatures of that earlier epoch. Less iron, less calcium, less of the heavy elements that only accumulate in a galaxy's gas supply over billions of years of stellar birth, nuclear burning, and death. The thin disk and the thick disk are not sharply separated boundaries. They are populations that blend into each other, distinguished by kinematics and chemistry rather than position. The astronomer Walter Baade first drew this distinction in 1944, working with the then new capabilities of large reflecting telescopes and careful star counts. He called the younger, metal-rich population Population 1 and the older, metal-poor population Population 2. The labels have remained in use ever since, though the details have been refined enormously. What drives the distinction is time. Stars that formed early in the galaxy's history emerged from gas that had not yet been enriched by many generations of stellar death. They are therefore metal-poor. Stars that formed later inherited a progressively more enriched interstellar medium. The age of a star and the abundance of its heavy elements are, in a rough but reliable way, correlated. Exactly when the thick disk of the Milky Way formed was a question that remained uncertain until recently. Mei Shengxiang and Hans Walter Rix, working with data from the Lamoste Spectroscopic Survey, covering approximately 250,000 subgiant stars, published a result in Nature in 2022 that placed the answer with unusual precision. The thick disk began forming approximately 13 billion years ago, only 800 million years after the Big Bang. The galaxy was barely a toddler when the first thick disk stars ignited. The stars that formed in that earliest phase encountered an interstellar medium that was thin in heavy elements and rich in hydrogen and helium, the original composition of the universe, barely touched by nucleosynthesis. 3I Atlas formed when the thick disk itself was young. The connection between an object's velocity and its age is the key tool that allows astronomers to make this claim quantitatively. Stars are not born with random velocities. They form from cold gas clouds that share the galaxy's organized rotational motion. And they begin their lives on relatively circular, low-eccentricity orbits. Over time, gravitational encounters with molecular clouds, with the spiral arms of the galaxy, with passing clusters of stars, gradually scatter the orbits of these stars, adding random components to their velocities. The older a stellar population, the more it has been scattered, and the broader the spread of velocities within that population. This is the age-velocity dispersion relation. It is a well-calibrated statistical tool, and it runs in both directions. If you know the velocity of an object, you can estimate the probable age of the population it belongs to. The velocity components of 3I Atlas, relative to the local standard of rest, the average motion of nearby stars, are precisely measured from its orbital solution. The component in the direction pointing toward the galactic center is negative 51 kilometers per second. The component in the direction of galactic rotation is negative 19.2 kilometers per second. The component perpendicular to the galactic plane, the vertical velocity, which is the most diagnostic for the age-velocity relation, is plus 18.5 kilometers per second. That vertical component is high. Stars with large velocities perpendicular to the galactic plane have been scattered far from the midplane by repeated gravitational encounters over billions of years. An object with a vertical velocity of plus 18.5 kilometers per second does not belong to a young stellar population. It belongs to the dynamically hot ancient population of the thick disk. Shokruz Kakarov and Abraham Loeb at Harvard used these velocity components to integrate 3I Atlas's orbit backward through a model of the Milky Way's gravitational potential, running thousands of Monte Carlo simulations to account for uncertainties in the orbital solution. The vertical excursion of the reconstructed orbit, how far above and below the galactic midplane the trajectory swings, is used as a proxy for the age of the source population. The result was a median age of 9.6 billion years, with a 68% confidence interval spanning 7.8 to 10.3 billion years. Matthew Hopkins at the University of Oxford, working with a different methodology but the same underlying principle, found a consistent result. Both analyses agree 3I Atlas is ancient. For comparison, 1I Oumuamua has an inferred age of approximately 1 billion years from the thin disk, from the era of recent star formation. 2I Borisov is approximately 3.8 billion years old, also thin disk, from roughly the same era as the solar system. 3I Atlas, at 9.6 billion years, predates both of them by an enormous margin. When the solar system formed 4.6 billion years ago, 3I Atlas had already been traveling through interstellar space for 5 billion years. The parent star of 3I Atlas, whatever star it orbited before being flung into the interstellar medium, was almost certainly a low metallicity star, with a heavy element abundance at least 40% below that of the Sun. This has consequences for the chemistry of any planetary system that formed around it. Fewer metals means fewer building blocks for rocky planets. Different ratios of carbon to oxygen in the protoplanetary disk mean different kinds of volatile ices, different distributions of molecular species, different conditions for planet formation than anything our solar system experienced. The chemistry of 3I Atlas is consistent with all of this. The carbon dioxide dominance, the extreme deuterium enrichment, the low carbon-13 abundance. These are not surprising if the object formed in a metal-poor disk around an ancient star. They are, in fact, predicted by it. Knowing the approximate age and the probable stellar population of the parent system narrows the portrait considerably, but it does not identify a specific star. And the reason for that, it turns out, is a matter of basic physics. 3I Atlas has been in interstellar space for up to 10 billion years. During that time, it has been scattered by encounters with stars, molecular clouds, and the large-scale gravitational structures of the galaxy itself. Each encounter slightly perturbs its trajectory. Over 10 billion years, those perturbations accumulate into something that effectively erases the original path. The trail back to the parent star has been destroyed, not by any single dramatic event, but by the patient, relentless work of gravity operating across geological time. Yiyang Guo and collaborators tested this directly. Working with precise astrometry from the Gaia satellite, and they integrated 3I Atlas's orbit backward for 10 million years, the practical limit of what can be done reliably with current stellar position data, and identified 62 high-confidence stellar encounters during that window. Not one of those encounters produced a meaningful perturbation on 3I Atlas's trajectory. The strongest perturber came within roughly 1/3 of a parsec and induced a velocity change of approximately 5/10,000ths of a kilometer per second. That is negligible. 3I Atlas's current orbit cannot be attributed to any encounter with any star currently known to us. The standard explanation for how interstellar objects like this one come to exist is giant planet scattering. The Sean Raymond and collaborators showed that 90% or more of the planetesimals that form in a protoplanetary disk are eventually ejected into interstellar space through successive gravitational encounters with giant planets. In our solar system, Jupiter is the dominant engine of this ejection. It throws debris onto hyperbolic orbits with each close encounter. Every star system that forms giant planets generates its own outward-flowing stream of ejected planetesimals. 3I Atlas was almost certainly one such fragment, flung from its parent system by a giant planet encounter in the early history of that system before the Sun existed. There is, however, a second possibility that the chemistry of 3I Atlas makes relevant. Brad Hansen and Ben Zuckerman proposed in 2017 that a significant population of interstellar small bodies must be produced by a completely different mechanism: post-main sequence stellar evolution. When a star like the Sun exhausts its nuclear fuel, it expands into a giant, sheds its outer layers, and collapses to a white dwarf. In doing so, it loses roughly half its mass. That mass loss destabilizes the orbits of any bodies in wide orbits around the remnant, Oort cloud analogues, extended reservoirs of icy planetesimals, and releases them into the galaxy. Bodies ejected this way are called durads. Given 3I Atlas's age, its parent star has almost certainly already died, probably billions of years ago. It may well be a durad, but there is a tension. when a star dies? Was the intense radiation and stellar winds of its final phases heat any material in the surrounding system to high temperatures? This thermal processing should strip away the most volatile ices: hydrogen, helium, methane. Yet 3I Atlas retains methane in notable abundance. This inconsistency between what Durad formation should produce and what 3I Atlas actually shows is unresolved. It may mean the object was ejected by a giant planet before the parent star reached its final stages. It may mean the methane was preserved in the interior, shielded from the heat by an insulating outer layer. It may mean something else entirely that no one has yet proposed. What the composition does provide, even without a specific parent star, is a portrait. Formation beyond the carbon dioxide frost line, when formation at temperatures below 30 Kelvin, a metal-poor environment, carbon chain depletion. These properties together constrain the kind of disk this object formed in, even if they cannot identify the disk, and they point consistently toward a single picture. An ancient, cold, low metallicity, protoplanetary disk circling a star that burned billions of years before the Earth existed. The galaxy may be full of that star's other children. Theoretical modeling by Forbes and collaborators suggests that objects ejected from a single planetary system spread through the galaxy over time in coherent braided streams, filaments of debris from a common source, winding through the Milky Way for billions of years. 3I Atlas may have siblings. They may be ahead of it in the stream or behind it. We have never detected one of these streams. We may, with the next generation of survey telescopes, finally do so. All of that, the ancient age, the dead parent star, the braided streams of galactic debris, is reconstruction after the fact. What actually happened on the 1st of July 2025 was considerably more mundane. A telescope in the Chilean desert recorded a faint moving point of light, flagged it as a candidate unusual object, and submitted the observation to a database. The chain of discovery that followed, unfolding over the next 7 weeks, is a story about how modern astronomy actually works. Networks of instruments, distributed across continents and orbit, feeding data into systems that were never specifically designed to find things like this, and occasionally finding them anyway. The Asteroid Terrestrial Impact. Last Alert System operates a network of survey telescopes whose primary mission is planetary defense. It watches the sky for asteroids on collision courses with Earth, generating alerts that are processed automatically within minutes of each exposure. Its telescope at Rio Hurtado in Chile, run by a team led by Larry Deno, was the one that caught 3I Atlas first. But the object had been in the data for much longer than anyone initially realized. Within hours of the first alert, Sam Dean, an amateur astronomer working through the same archival data, had found earlier detections going back to the 5th of June. That is 26 days of undetected crossing, most of it happening in front of one of the most crowded regions of sky visible from Earth. The star fields near the galactic center are dense enough with background sources that automated detection algorithms had repeatedly discarded the moving point as noise. The 5th of June pre-discovery image showed only the very beginning of cometary activity. By the time the object was officially logged on the 1st of July, it had been active for nearly 2 months. The Vera C. Rubin Observatory had also been watching, without knowing it. The world's most powerful survey telescope was in its commissioning phase in the spring and summer of 2025, taking test observations across large swathes of sky in preparation for the full legacy survey of space and time that would soon begin. Colin Orion Chandler and collaborators recovered 3 Eye Atlas from Rubin, commissioning data beginning on the 21st of June. What those images showed was the coma growing in real time, 13,000 kilometers across on 21st June, 18,760 kilometers across on 2nd July. 11 days of documented growth, captured serendipitously by a telescope that happened to be pointing in the right direction during the most significant interstellar visit in the history of sky surveys. By the 2nd of July, 122 individual observations had been submitted to the Minor Planet Center from 31 different observatories around the world. The trajectory was clear, the eccentricity was clear. The designation 3I, the third interstellar object, was assigned that day, alongside the formal comet designation that placed the object in the same category as the comets of our own solar system. The confirmation had taken less than 48 hours from the original alert to official naming. 3 weeks later, on the 21st of July, the Hubble Space Telescope turned toward the object and obtained the first high-resolution images. David Jewitt and his team saw the structure of the coma in detail for the first time. The teardrop shape, the sunward fan of material pointing toward rather than away from the star, the diffuse outer envelope that ground-based telescopes had only sketched in outline. The nucleus itself remained invisible. The dust and gas surrounding it were too thick and too active for even Hubble to resolve the solid body beneath. What the images could establish was a size constraint. The nucleus was no larger than 5.6 kilometers in diameter, and almost certainly smaller. How much smaller remained an open question. The sustained monitoring work that would eventually produce the clearest picture of the coma's structure and evolution was already underway in Tenerife. Miquel Serra Ricard and Javier Licandro, working with the 2-meter twin telescope at the Teide Observatory on the Canary Islands, began a dedicated imaging program on the 2nd of July that ran for 37 consecutive nights through to the 5th of September. Night after night, they tracked the evolution of the sunward fan as the object warmed and brightened on its approach, documenting a periodic wobble in the jet that would later constrain the orientation of the nucleus's rotation axis. Their campaign underpinned a paper in astronomy and astrophysics. The peer-reviewed result that gave the jet morphology a natural explanation consistent with ordinary cometary physics, driven by a discrete active region near the sunward pole of the rotating nucleus. In November, as the object re-emerged from behind the Sun after perihelion, Bryce Bolin led a program with the Gemini North Telescope on Mauna Kea in Hawaii, obtaining color images through the Gemini Multi-Object Spectrograph. Those images showed the coma's post-perihelion transformation clearly. The reddish dust of the early months had given way to a green glow, diatomic carbon fluorescing under solar ultraviolet light, a signature of vigorous gas chemistry. The comet had passed through the hottest part of its journey and survived, and the story of what it had shown the world during that passage was only beginning to be written. At 11:45 Universal Time on the 29th of October 2025, 3I Atlas reached the closest point in its passage to the Sun. 1.356 astronomical units, inside the orbit of Mars, outside the orbit of Earth, in the empty zone between two planets. The object was moving at 68 kilometers per second relative to the Sun. This was the peak of its speed through our solar system, the moment of maximum gravitational acceleration as it swung around the star, and it was, in all probability, the closest any star had come to this object in 10 billion years of travel. What a star does to an icy body is not subtle. Solar radiation heats the sunward face. Volatiles sublimate and stream outward. Dust is carried with them. The sunward side heats faster than the night side, creating asymmetric outgassing. Jets of gas and particles driven preferentially toward the sun and then swept back by radiation pressure into the tails. As the object warms, more layers of ice are exposed. More volatiles are released. The activity that TESS had detected as early as May, at a distance of 6.4 astronomical units, was modest compared to what perihelion brought. At perihelion, the comet was at its most violent. Its chemistry was exposed in full, and the heat it was receiving was, for this particular object, entirely unprecedented. The thermal inertia of the nucleus means that peak activity does not occur at perihelion itself. The nucleus takes time to heat through. The deepest ice deposits respond slowly to the change in solar flux, and the maximum outgassing rate arrives after the closest approach, not at the moment of it. For 3I Atlas, the peak in water production was reached approximately 1 week after perihelion. At that point, water molecules were being released at a rate of approximately 3.17 times 10 to the power of 29 molecules per second. That is a number that is difficult to hold in the mind. It corresponds to roughly 1.5 trillion tons of water per day, streaming off the nucleus and into the coma. For an object that had not encountered a significant source of heat since it was ejected from its parent system, which is to say, and for an object that had been frozen near absolute zero for perhaps 10 billion years, this was a first. As the object had brightened through September and October, observers at ground-based telescopes noticed a shift in the color of the coma. The reddish hue of the earlier months was giving way to something blue-green. In some coverage, this was described as a mysterious color change, implying an alteration in chemistry or some dramatic new event. Qicheng Zhang at the Lowell Observatory corrected the record. The coma had contained a gas component with a blue-green signature since at least September. The color came from diatomic carbon molecules fluorescing under solar ultraviolet radiation. As the comet brightened on its approach, the gas emission became bright enough to visually dominate the reddish dust reflection. Nothing had changed in the chemistry. The balance of what was visible had shifted. It was entirely normal cometary behavior. The comet had always been talking in both registers at once. None of this was visible from Earth directly. By late October, as 3I Atlas made its closest approach to the Sun, the star itself had swallowed it from any ground-based observer's perspective. On the 21st of October, the solar elongation, the angular separation between the object and the Sun as seen from Earth, reached a minimum of 2.59 degrees. The object was effectively lost in the solar glare. Perihelion came and went unseen from Earth's surface. The eyes that were watching were not on Earth. 3I Atlas made its closest approach to Mars on the 3rd of October 2025, now passing within approximately 29 million kilometers of the planet. Shannon Curry's team at the University of Colorado used NASA's MAVEN spacecraft in orbit around Mars to map the hydrogen clouds surrounding the comet using ultraviolet instruments. The Mars Reconnaissance Orbiter's HiRISE camera, designed to image rocks on the Martian surface, was turned outward and used to capture the closest spacecraft images of 3I Atlas obtained during the perihelion passage. The European Space Agency's ExoMars Trace Gas Orbiter also observed the comet and contributed astrometric measurements to the Minor Planet Center, the first time a spacecraft orbiting another planet had formally contributed to that database. The result was a 10-fold improvement in trajectory accuracy. The international infrastructure of planetary science, built for entirely different purposes, turned to face a visitor from another star. something else emerged from the perihelion data. Davide Farnocchia at the Jet Propulsion Laboratory, working through astrometry that included measurements from the Atacama Large Millimeter Array, found that 3I Atlas had deviated from its predicted gravitational position by approximately 4 arc-seconds in right ascension at perihelion. The object was not where gravity alone said it should be. A subsequent analysis by Spada, Krolikowska, and Dones confirmed non-gravitational acceleration, components both radial and normal to the orbit, consistent across multiple independent orbital solutions. The natural explanation was the rocket effect, asymmetric outgassing from the intensely heated nucleus, creating a net thrust. The magnitude was consistent with the directional activity observed at closest approach. The comet, in the most literal sense, was pushing itself. Every instrument that could be pointed at it was running. Every data stream was open. And still, the closest approach itself had happened out of sight. The observation campaign that surrounded 3I Atlas during its passage through the solar system was, by most measures, the most comprehensive ever assembled for a comet. More than 20 NASA instruments alone contributed data, alongside assets from the European Space Agency, from Japan's Space Agency, from the European Southern Observatory, and from dozens of ground-based facilities across 5 continents. The instruments covered the electromagnetic spectrum from radio wavelengths through to X-rays. Each was chasing a different piece of the same object. Each was operating under the same constraint. When the object left, there would be no second opportunity. The most operationally striking contribution came from a spacecraft that was not designed to observe comets at all. The European Space Agency's JUICE mission, en route to Jupiter to study its icy moons, was redirected to observe 3I Atlas through a sustained engineering effort led by spacecraft operations manager Angela Dietz. The effort took 4 months from scratch, configuring 5 of the spacecraft's science instruments for an object and geometry they had not been built to study, calculating pointing sequences for a target moving at extraordinary speed, and testing procedures on a spacecraft hundreds of millions of kilometers from any engineer who could intervene if something went wrong. JUICE came closer to 3I Atlas in its most active period than any other spacecraft came to the object at any point in its passage. The 5 instruments it turned toward the comet included the Janus Science Camera, the MAGIS infrared and visible spectrometer, the ultraviolet spectrograph, the submillimeter wave instrument, and the particle environment package, an array covering imaging, composition, and the particle environment simultaneously. The data were collected. Then the spacecraft's thermal management system held them in storage for months, unable to downlink until the geometry permitted. They arrived on the 17th and 20th of February 2026. The Janus images showed a clear tail and coma structure. The compositional instruments revealed data that were still being analyzed as this account was being assembled. The heliophysics fleet contributed from a different direction. The Parker Solar Probe, diving toward the Sun on its primary mission, carried an instrument called the Wide Field Imager for Solar Probe, known as WISPR, a wide-angle camera designed to image the solar corona. Between the 18th of October and the 5th of November 2025, WISPR captured 3I Atlas in its field of view through the perihelion window, imaging the comet's dust tail against the backdrop of the solar wind environment. The polarimeter to unify the Corona and Heliosphere mission, known as PUNCH, along with the Solar Terrestrial Relations Observatory and the Solar and Heliospheric Observatory, all contributed observations during the same period. These spacecraft existed to study the Sun. They found an ancient interstellar visitor in their data, as a secondary consequence of doing their intended work. The X-ray observations opened a window that had never been applied to an interstellar object before. Japan's X-ray imaging and spectroscopy mission observed 3I Atlas in late November 2025. The European Space Agency's XMM Newton followed with a dedicated 20-hour observation on the 3rd of December. Both detected the diffuse X-ray glow produced by solar wind charge exchange with neutral molecules in the cometary atmosphere. The significance here is not only what the glow confirmed about the coma's density, it is that the technique worked at all. The next interstellar visitor, whenever it arrives, can be observed with X-ray telescopes. A new observational window has been demonstrated. From the ground in South Africa, the Meerkat Radio Telescope Array detected hydroxyl in the radio spectrum, the product of water molecules broken apart by solar ultraviolet light, each fragment retaining a characteristic radio signature. Alongside the Meerkat detection, the Breakthrough Listen program conducted a systematic search for any artificial radio emission from the object. The search found nothing. The upper limit on any transmitting source was 0.17 watts at the object's distance, approximately the power output of a mobile phone handset. 3I Atlas was not broadcasting. Whatever it was not an antenna. The remaining instruments completed the portrait. Hubble set the upper limit on the nucleus diameter and provided ultraviolet spectroscopy of the coma. The James Webb Space Telescope delivered the volatile chemistry and the isotopic ratios. Sphere-X mapped the extended carbon dioxide coma and detected water ice in absorption. The Neil Gehrels Swift Observatory measured hydroxyl emission and provided independent water production rate estimates across the apparition. TESS supplied the rotation period and the pre-discovery photometry, showing the comet active at 6.4 astronomical units back in May. Between them, these instruments covered the object from radio to X-ray and built the most complete multi-wavelength portrait ever assembled of an interstellar visitor. Geraint Jones, the principal investigator of the European Space Agency's Comet Interceptor mission, a spacecraft already in space, parked at the Sun-Earth Lagrange point and waiting for a suitable comet, described the 3I Atlas campaign as the clearest possible demonstration of what a purpose-built interceptor would exceed. Every instrument in this chapter was improvised, adapted, or repurposed. The results were extraordinary. What a spacecraft designed from the outset to intercept an interstellar object might return, flying through the coma, sampling the gas and dust directly, imaging the nucleus from a few hundred kilometers, remained the question that the entire scientific community was already asking. The answer, if it came at all, would require the next visitor to arrive at the right time. And the next visitor, on the evidence of how quickly the field had changed since 2017, was perhaps not as far away as it had once seemed. When a comet is active, seeing the nucleus is like trying to see a candle flame inside a bonfire. The coma, the cloud of gas and dust shedding off the nucleus, contributes more than 90% of the total optical brightness. The nucleus itself, a few kilometers of ancient ice and rock, is buried inside its own output, invisible behind the light it has generated. Finding it requires not just a sensitive telescope, but a technique, modeling the expected brightness distribution of the coma across the image, subtracting that model from the data and looking for any residual brightness at the center that cannot be accounted for by the coma alone. The method is called point spread function subtraction, and it demands precise, repeated observations across multiple geometries over a long enough period to distinguish a genuine compact source from the surrounding glow. Manta Hui and collaborators applied this technique to Hubble Space Telescope observations spanning July through November 2025. 6 months of carefully modeled images covering different viewing geometries as the Earth moved in its orbit around the Sun. The work was patient and technically demanding. The result was the first direct detection of the nucleus of any interstellar object ever observed. The effective diameter was 2.6 kilometers, with an uncertainty of plus or minus 0.4 kilometers. An object that had been invisible behind its own exhalations since the moment of discovery finally appeared as a discrete, bounded body. The size was consistent with an independent measurement derived from a completely different source. The non-gravitational acceleration measured at perihelion, the deviation from a purely gravitational orbit confirmed by Spada, Krolikovska, and Donis, placed a constraint on the nucleus mass. If asymmetric outgassing from the measured surface area produced the observed acceleration, the implied mass was approximately 4.4 times 10 to the power of 10 kilograms. For a body of roughly 2.6 kilometers in effective diameter, at the densities typical of cometary nuclei, that mass is consistent. 2 methods, 2 datasets, 1 answer. The comparison with the 2 previous interstellar objects is stark. 2I Borisov had a nucleus of approximately 400 meters. 3I Atlas, at 2.6 kilometers in effective diameter, is roughly 40 times more massive. 1I Oumuamua, an object estimated at roughly 100 meters in its longest dimension, is at least 20,000 times less massive than 3I Atlas. These are not comparable objects in any size sense. 3. I arrived at a different scale entirely. Something was also happening to the nucleus that had no precedent in interstellar object science. Pre-perihelion. The rotation period of the nucleus was 16.16 hours, a leisurely, slightly longer than Earth day rotation. By late January 2026, that period had fallen to approximately 7.1 hours. The nucleus had more than doubled its rotation rate in 3 months. The cause was the jets themselves. As the comet heated and outgassed asymmetrically, the reaction from each jet applied not just a linear push along the orbit, but a torque, a rotational kick that varied as different active regions came in and out of sunlight. Over weeks and months of sustained, directional outgassing, those kicks accumulated into something measurable and dramatic. The nucleus was being spun up by its own activity, faster and faster as it moved through the inner solar system, and the heating intensified. In post-perihelion images, Tony Scarmato identified 3 distinct mini-jets in the coma, each separated from the next by approximately 120 degrees, a near-perfect threefold symmetry around the nucleus. All 3 wobbled together with the 7.1-hour rotation period, tracing out the rotation of the active regions beneath them. The geometry placed the rotation axis within approximately 20 degrees of the sunward direction, nearly aligned with the Sun. The astronomy and astrophysics paper, produced from the Tenerife campaign, the 37-night monitoring effort by Sarah Ricard and Licandro, had reached consistent conclusions from the pre-perihelion data, identifying a discrete active source at approximately plus 75 degrees latitude on the nucleus as the primary driver of the observed jet wobble. There is an open question embedded in all of this. A rotation period of 7.1 hours for a body 2.6 kilometers across generates centrifugal forces at the equator that are not trivial. As rotation rate increases, the outward force increases. Whether the nucleus will fragment depends on its internal tensile strength, the degree to which its ice and rock are bound together rather than loosely aggregated. That property cannot be measured remotely. As observations continued in the weeks and months after perihelion, the nucleus had not broken apart. Whether it eventually would remain open, the object that had survived 10 billion years in interstellar space was being tested for the first time by a star. The story of 3I Atlas becomes more legible when it is placed alongside the two objects that came before it. 1I Oumuamua arrived in our solar system in 2017, discovered by the Pan-STARRS telescope in Hawaii. Karen Meech led the team that published the discovery. What they found defied easy categorization. The object had an extreme elongated shape, at least 10 times longer than it was wide, perhaps more. It showed no detectable coma and no outgassing, yet it was accelerating away from the sun faster than gravity alone could account for, with no visible source of propulsion. Solar system comets sometimes accelerate through asymmetric outgassing, but there was no coma to generate the force. The mystery attracted a disproportionate amount of public attention, not all of it scientific in tone, and it produced a genuine debate within the research community about the limits of what remote observation can and cannot determine. In the years that followed, a series of hypotheses was advanced. A nitrogen iceberg eroded from the surface of a Pluto-like world, a hydrogen iceberg too cold to emit visible emissions, a fractal dust aggregate pushed by radiation pressure despite its tiny mass. None commanded a consensus. 1I Oumuamua remained at bottom, an object the field could not fully explain. Its inferred age was approximately 1 billion years, placing it in the young thin disk from the era of recent star formation in the solar neighborhood. 2I Borisov arrived in 2019 and discovered by amateur astronomer Gennady Borisov from his private observatory in Crimea. From the first observation, it was clearly a comet, active, diffuse, with a visible coma and a tail. Where 1I had refused to behave like anything familiar, 2I Borisov behaved almost entirely like a conventional solar system comet, right down to a slight fragmentation after perihelion. It was extraordinarily carbon monoxide rich, suggesting it had formed in the cold outer regions of its parent protoplanetary disk, far from its star. Its nucleus was approximately 400 meters across. Its inferred age of approximately 3.8 billion years placed it in the thin disk at roughly the same cosmic epoch as our own solar system, a neighbor in time, a stranger in space. The familiarity of 2I Borisov was almost a relief after the bewilderment of 1I. Here was something the solar system had trained us to recognize. 3I Atlas was neither of these things. It was larger than both by an enormous margin. It was older than both by an enormous margin. It was more chemically complex, more isotopically extreme, more compositionally alien than either. The three objects together span roughly 10 billion years of galactic history, and each carries the imprint of its own era. 1I from the young thin disk, when the Milky Way's spiral arms were building their current stellar populations. 2I from the solar system age thin disk, from a neighborhood that would not have looked very different from our own in terms of stellar composition and heavy element abundance. 3I from the ancient thick disk, from an epoch before the sun existed, when the galaxy was still young and its first stellar generations were seeding the interstellar medium with heavy elements for the first time. Each object is a sample of what planet formation looked like in a different chapter of the galaxy's history. David Jewett and Darrell Seligman, reviewing the three objects together, described the progression as reading the galactic record in 3 data points. What you see is not repetition. What you see is range. There is, however, a problem embedded in that range. In our own solar system, The number of objects at any given size follows a well-established distribution. Smaller objects are far more numerous than larger ones, scaling steeply with decreasing size. If interstellar objects follow a similar distribution, which models of planet formation and ejection strongly predict, then for every object at 3I Atlas's scale, there should be vastly more objects in the size range between 1I and 3I, between 100 meters and 2.6 kilometers, an intermediate population. Yet in 8 years and 3 confirmed interstellar visitors, not one object in that intermediate range has been detected. 1I is very small. 3I is relatively large. The middle is empty. This is either telling us something genuine about the size distribution of interstellar objects, that it is flatter than predicted, with large and small more equally represented than in our own solar system, or it is telling us something about the limits of our detection capability. Objects at a few hundred meters, is moving at interstellar speeds, are exceptionally faint and fast-moving. The survey telescopes that found the 3 confirmed visitors were not purpose-built for this search. The Vera C. Rubin Observatory, now operational and conducting the legacy survey of space and time with sensitivity and cadence far exceeding any predecessor, is expected to detect interstellar objects in meaningful numbers within years. Whether the intermediate population exists or is simply hidden, the answer is coming. 3 confirmed interstellar visitors in 8 years. The natural question that follows is not about these 3 objects in particular. It is about the population they represent. How many are out there right now, moving through our solar system unseen? How many are in the galaxy as a whole? And what does finding them at the rate we have found them require to be true about the history of planet formation across the Milky Way? The detection rate provides a starting point. 2 large interstellar objects, 2I Borisov and 3I Atlas, both approximately the same size class, were detected within 6 years, using survey facilities that covered a known volume of sky to a known depth. From those numbers, astronomers can calculate an implied number density, the average number of objects of this scale per unit volume of space in the solar neighborhood. The result is approximately 3 times 10 to the power of -4 objects per cubic astronomical unit, a number that sounds abstract until you work out what it implies for the solar system as a whole. At any given moment, there are approximately 60 interstellar objects of roughly this size class within Jupiter's orbit, moving through the inner solar system on hyperbolic trajectories we have not detected. Of those, roughly 8 may be temporarily gravitationally captured, held in loosely bound orbits by Jupiter's gravity, orbiting for a time before eventually escaping. On average, a new object of approximately 10 kilometers in effective diameter crosses inside Jupiter's orbit once every 5 years. These are not predictions from theoretical models. They are inferences from the actual survey data. The visitors are continuous. We are simply not seeing most of them. The galactic population implied by these local numbers is staggering. David Jewett and Darrell Seligman, working through the population statistics in a review published in 2023, estimated the total number of similar interstellar objects in the Milky Way at approximately 10 to the power of 25 to 10 to the power of 26. 10 to the power of 25 is 10 million billion billion. These objects, at this population level, are the most numerous macroscopic bodies in the galaxy, more numerous than stars by a factor of roughly 10 trillion, more numerous than planets by a factor that dwarfs any useful comparison. The galaxy is not mostly stars and planets and nebulae. It is mostly dark, cold, wandering ice and rock, a vast, silent population of planetary debris cast out over the full history of star formation, drifting on trajectories set billions of years ago by gravitational encounters no observer recorded and no instrument measured. Producing that population requires mass. Matthew Hopkins and collaborators worked backward from the observed number density to ask how much material each star system must have ejected to account for what we are finding. The answer is approximately 1/100th of a solar mass in objects at 3 I-Atlases scale and larger per stellar system over the history of the galaxy. 1/100th of a solar mass is roughly 10 times the mass of Jupiter. Every star system that has formed planets has, on this accounting, flung the equivalent of 10 Jupiters worth of material into interstellar space in objects of this scale alone. The raw material that failed to become planets did not disappear. It became the galaxy's background of wandering debris, and some of it, over billions of years, finds its way into other systems. The instrument that will transform this field from the study of remarkable individuals into a genuine population science is now operational. The Vera C. Rubin Observatory, conducting the legacy survey of space and time, will systematically scan the sky to a limiting magnitude of approximately 24.5, several times fainter than the surveys that found 2I and 3I. Michelle Bannister at the University of Canterbury has projected that at this sensitivity, combined with the survey's cadence of returning to the same sky region every few nights, the discovery rate for interstellar objects could reach dozens per year once the survey is fully underway. The field is not waiting for a new discovery. It is waiting for the first season of results. There is one further dimension to the population question that the dynamics of galactic travel make unavoidable. Objects ejected from a single planetary system do not disperse randomly through the galaxy. Forbes and collaborators showed in 2024 that they propagate in coherent braided streams, filaments of debris from a common source, bound together by the shared velocity imparted at ejection, winding through the Milky Way over billions of years. The implication is striking. If 3I Atlas came from a specific parent system, there may be other fragments from that same system already in transit, earlier arrivals that passed through our solar system millions of years ago, later arrivals that will not reach us for millions more. Statistically, the Rubin survey may eventually identify these streams by looking for clustering in the incoming velocities of newly detected interstellar objects. The debris of a dead star system arriving in sequence might finally allow us to characterize a planetary system we can never directly observe. What 3I Atlas preserves is not just a record of one object. It is a physical sample of the conditions that existed in the Milky Way 10 to 12 billion years ago, before the solar system existed, before most of the galaxy's current stellar population had formed. The thick disk of the Milky Way, as the Xiang and Rick study established, began forming approximately 13 billion years ago, only 800 million years after the Big Bang. In the early epoch of the thick disk, star formation was intense and chaotic, and massive stars formed rapidly, burned briefly, and died in supernovae that seeded the surrounding interstellar medium with heavy elements for the first time. The chemical environment was unlike anything that exists in the galaxy's disk today, poorer in metals, richer in hydrogen and helium, with different ratios of carbon to oxygen and nitrogen to sulfur than the gas from which the Sun and its planets eventually formed. 3I Atlas accreted in that environment. Its chemistry carries the signature of those conditions directly, not as an inference from stellar models, but as a measurement of the actual material that condensed in an actual protoplanetary disk at that time. But the object we observed was not the pristine product of that ancient disk. It was the product of 10 billion years of cosmic ray processing as well. So galactic cosmic rays, high-energy charged particles streaming continuously through interstellar space, penetrate solid bodies to depths of approximately 15 to 20 meters. Over billions of years of exposure, they chemically transform the material in that zone, breaking molecular bonds, creating new compounds, building up the dark, complex, reddish organic material called tholins. The outer shell of 3I Atlas, by the time it arrived in our solar system, had been irradiated for 10 billion years. What the pre-perihelion optical spectroscopy measured was not the original protoplanetary disk chemistry. It was that chemistry, modified by a geological era of cosmic ray bombardment. The post-perihelion evolution made this layered structure visible. As solar heating stripped away the outer processed shell, the chemistry changed. The carbon chain depletion became less severe. Methane emerged. Metal production rates shifted. The progression was consistent with layers of progressively less altered material being exposed as the surface eroded, the ancient disk chemistry becoming more legible as the processed overburden was removed. It was, in a sense, an archaeological excavation conducted by the Sun. The isotopic ratios survived this processing intact. Deuterium enrichment in the water and methane was set at the moment of molecular condensation in the cold, shielded disk, mid-plane, 10 billion years ago. Cosmic ray bombardment altered the surface chemistry, but did not reach deep enough to reset the bulk isotopic composition of the interior ice. What Cordner and Roth measured in 2026 was therefore a signal of extraordinary antiquity, the oldest directly measured isotopic fingerprint of protoplanetary disk chemistry ever obtained. We do possess other physical samples from outside our solar system. Pre-solar stardust grains, microscopic particles of silicon carbide, graphite, and other minerals found embedded in the most primitive meteorites, formed in the outflows of ancient stars before the solar system existed. They are genuine samples of other stellar environments, and they have yielded remarkable science. But they are micron-scale mineral particles, each preserving the chemistry of a single stellar atmosphere at a single moment. 3I Atlas is something categorically different, a kilometer-scale body from another planetary system, preserving the bulk volatile chemistry of an entire protoplanetary disk. The comparison is between a grain of sand and a boulder. Both are real. Only one tells you what the beach was made of. The molecular inventory of 3I Atlas's coma, hydrogen cyanide, methanol, methane, water ice, and complex organics, is the inventory of prebiotic chemistry. These are the molecules that, under the right conditions of temperature, pressure, ultraviolet irradiation, and liquid water, participate in the reactions that produce amino acids, nucleobases, and the building blocks of living systems. 3I Atlas did not strike any planet in our solar system, but it has been in transit for 10 billion years, and it has passed through countless other stellar systems on its journey. Whether the molecular cargo it carries has ever been delivered to a planetary surface, and whether any of it has ever contributed to the chemistry of a world capable of using it, is a question that cannot be answered and may never be. What can be said is this: the same molecules that preceded life on Earth are present in an object that formed before the Earth existed, in a star system that lived and died before the Sun ignited, and that has been carrying them across the galaxy for longer than our planet has been solid. The question of whether an interstellar object might be of artificial origin is not a fringe question. It has a legitimate scientific history. Robert Freitas and Francisco Valdés proposed the theoretical framework for detecting interstellar probes in 1985 as part of the broader search for extraterrestrial intelligence. Their argument was simple. If any civilization in the galaxy has the technology to send physical probes to other star systems, those probes would arrive here as objects on hyperbolic trajectories, indistinguishable from a distance from natural interstellar objects. When a new interstellar object is discovered, asking whether its properties are consistent with natural or artificial origin is not sensationalism, it is due diligence. 3I Atlas generated that question in earnest. The case for scrutiny rested on 3 categories of observation: the orbital geometry, a retrograde trajectory nearly opposite to planetary motion, approaching from the direction of the galactic center, with multiple close planetary encounters during the passage, and the coma morphology, the collimated sunward jet, the asymmetric structure, the periodic wobble that some interpreted as directional control, the chemical profile, the extreme carbon dioxide dominance, the initial nickel anomaly, the extraordinary deuterium enrichment. Each of these, in isolation, has a natural explanation. Whether they were more significant in combination was the contested question. Here is what the peer-reviewed evidence actually established, working through each category in turn. On the orbital geometry, unusual trajectories are not diagnostic of artificial origin. The retrograde inclination of 175 degrees is striking, but retrograde orbits are possible outcomes of isotropic interstellar infall. And the probability arguments advanced to suggest the orbital properties were improbably coincident are vulnerable to a well-known statistical trap. Calculating the odds of a specific configuration you have already observed and treating that calculation as evidence of design. The Serra-Ricard and collaborators' paper in Astronomy and Astrophysics, the primary peer-reviewed treatment of the jet morphology, found the wobble period and rotation axis orientation fully consistent with a carbon dioxide-driven active source at approximately plus 75 degrees latitude on a naturally rotating nucleus. There is no orbital or morphological feature in the data that requires an explanation beyond cometary physics. On the non-gravitational acceleration, T, Marshall Eubanks and collaborators analyzed the measured acceleration components and found them within the normal range expected from asymmetric cometary outgassing. Darrell Seligman, who had published the first formal early galaxy environment. The chemistry is not merely consistent with natural origin, it is precisely what models of cometary formation in the early thick disk predict for an object of this age. The deuterium enrichment is not anomalous given a formation temperature below 30 Kelvin. The carbon dioxide dominance is expected for an object that formed beyond the carbon dioxide frost line in its parent disk. The nickel to iron ratio normalized with temperature as the organometallic sublimation model predicts. None of these required an artificial explanation. All were explained by natural physics. The Breakthrough Listen program conducted the most comprehensive technosignature search ever performed on an interstellar object. The Allen Telescope Array, the Parkes-Murray-Yang radio telescope in 3 separate observing sessions, the Meerkat Array, and the Green Bank Telescope all searched for artificial radio emission across a wide range of frequencies. The Green Bank Telescope observation achieved a sensitivity capable of detecting a transmitter of approximately 0.1 watts at the distance of closest approach, roughly the power output of a mobile phone handset at approximately 270 million kilometers. 0 signals were detected at any frequency in any observation. Chris Lintott at the University of Oxford, David Kipping, Scott Manley, and many other researchers took the time to publicly identify specific methodological problems in the probability arguments that had been circulated in support of an artificial hypothesis. The errors were not minor quibbles. Had they included selecting properties to test after observation, a practice that systematically inflates apparent statistical significance, and comparing the object against a solar system baseline that is, by definition, the wrong reference population for an interstellar visitor, the consensus that emerged was clear. 3I Atlas is a natural comet. It is scientifically extraordinary. Its chemistry encodes the conditions of the early galaxy in ways that will take years to fully analyze. None of this requires an artificial explanation, and the natural explanation, properly understood, is more remarkable than the alternative. The technosignature question was asked rigorously. It was answered comprehensively. What remains is the science, and the science is far from finished. The science is also, for the first time, pointing toward what comes next. And what comes next has an engineering problem at its core. No spacecraft intercepted 3I Atlas. It crossed the inner solar system in months. At the time of discovery, it was already inside Jupiter's orbit, moving at 61 kilometers per second. By the time any spacecraft could have been designed, funded, built, and launched under those conditions, the object would have been beyond any reasonable intercept trajectory. The observation window closed while the mission was still a concept. 3I Atlas demonstrated, in the most concrete possible way, that the observational infrastructure to characterize interstellar objects is maturing rapidly, while the hardware to reach one remains a generation behind. What a spacecraft flying through 3I Atlas's coma at closest approach would have returned is not a refinement of the remote spectroscopic measurements. It is a different class of data entirely. Direct sampling of the outgassing material before solar radiation modifies its chemistry. Dust composition at the grain level, including isotopic ratios of individual particles. Close images of the nuclear surface, the geometry of the active regions, the layering of processed and unprocessed material, the features that drove the spin-up, the plasma environment immediately surrounding a body that has been in interstellar space for 10 billion years. These measurements are not achievable from a distance of 1.5 astronomical units with any telescope yet built. They require a spacecraft in the coma. The Comet Interceptor mission was designed with exactly this ambition in mind. A 3-spacecraft system built by the European Space Agency, with one probe provided by the Japan Aerospace Exploration Agency. It launched in 2029 as a co-passenger with the Ariel mission to study exoplanet atmospheres. Geraint Jones at the Mullard Space Science Laboratory is the principal investigator, and Colin Snodgrass is a lead scientist on the mission team. The 3-spacecraft architecture is deliberate. The main spacecraft conducts a distant flyby, while the 2 smaller probes are released to fly into or near the coma, surviving their encounter for as long as possible before being destroyed by dust impacts. The combined measurements will return a multi-vantage portrait of the target that no single spacecraft could produce. The mission is now parked at the Sun-Earth Lagrange point, the gravitationally stable zone approximately 1.5 million kilometers sunward of Earth, waiting. It will wait there for an appropriate target, ideally a dynamically new comet on its first approach to the inner solar system, or, if one is detected with sufficient warning, an interstellar object. The caveat in that last phrase is the engineering problem in miniature. 3I Atlas was moving at 61 kilometers per second relative to the Sun. Current launch vehicles, working with the best available mission design, can provide approximately 15 kilometers per second of velocity change from Earth. The gap between those numbers is not bridgeable with existing technology after discovery. Comet Interceptor is already pre-positioned, which helps enormously. It does not need to launch after detection, and its relatively modest velocity budget can match comets moving at speeds typical of dynamically new solar system comets. But interstellar objects moving at 50 or 60 kilometers per second are, for now, out of reach after discovery. Catching one requires either detecting it years before closest approach, so a dedicated mission can be planned, funded, and launched with time to intercept, or a future generation of spacecraft with substantially higher delta-v. The Vera C. Rubin Observatory changes the detection side of the equation. With the legacy survey of space and time detecting interstellar objects at potentially dozens per year, the probability of finding one early enough to plan an intercept improves dramatically. Michelle Bannister has noted that with a large enough sample of incoming objects, some will inevitably be detected far enough out, at distances of 10 or more astronomical units, to give an intercept mission years of lead time. The question is whether a spacecraft will exist that can use that lead time. The Comet Interceptor mission is the first answer. The next answer will require a step change in propulsion capability. What the Rubin era promises, beyond more objects, is the beginning of a genuine taxonomy. 3 confirmed interstellar visitors, 3 profoundly different objects. 1I Oumuamua still unexplained, 2I Borisov familiar and reassuring, 3I Atlas ancient and chemically extraordinary. Whether the 4th will resemble any of them is genuinely unknown, as the sample size is too small to draw population-level conclusions. With dozens of objects detected per year, the questions that have been asked individually — how common is carbon dioxide dominance? How typical is thick disk provenance? How often do interstellar objects arrive with extreme kinematic ages? — will become answerable statistically. The era of being astonished by individuals is giving way to the era of understanding the population. The next visitor is already in transit. How long it has been traveling, and what it is made of, and which dead star system sent it — those answers are coming. We have not yet sent anything to another star. The nearest one is 4 light-years away, a distance that no human-made object will cross in any lifetime now living, at any velocity we currently know how to achieve. The dream of interstellar exploration, in the sense of physical probes reaching other systems and returning data from them, belongs to the future in a way that makes it feel almost theoretical. And yet, the data has been arriving anyway. The galaxy did not wait for us to build the rockets. It has been conducting its own sample return program for billions of years, and the solar system has been one of the receiving ends all along. The logic of this was established long before we knew interstellar objects existed. Jan Oort proposed in 1950 that the solar system is surrounded by a vast spherical cloud of icy bodies at enormous distances from the Sun. The reservoir from which long-period comets originate, bodies that spend most of their existence in the cold dark at the outermost edge of the solar system's gravitational reach. Gerard Kuiper, in 1951, proposed a flattened belt of icy bodies just beyond Neptune, the remnant outer edge of the original protoplanetary disk. Both structures describe the same underlying reality. Planet formation produces far more small icy bodies than it assembles into planets, and most of the original protoplanetary material is either ejected into interstellar space or stranded in distant orbits where it waits, frozen and unchanged, for billions of years. The same physics applies to every other stellar system. Every system that has ever formed giant planets has scattered the overwhelming majority of its outer icy bodies into interstellar space. The ejection is not a failure of the system. It is the standard outcome of the process. When those systems age, the outward flow continues. A star dying and losing half its mass destabilizes the bodies in wide orbits, releasing the outer reservoir. Over the full history of the Milky Way, 13 billion years of star formation, planetary system assembly, stellar death and mass loss, this process has seeded interstellar space with a population of wandering bodies too numerous to count. We calculated earlier that approximately 10 to the power of 26 such objects fill the galaxy at any given time. That number means that the space between the stars is not a void. It is a slow, continuous rain of ancient planetary debris, most of it dark and cold and invisible, but all of it carrying the chemical record of the system that made it. The stream picture gives this a further dimension. The braided filaments of debris from individual parent systems, coherent flows of material that persist for billions of years, mean that the rain has structure. Material from a given system arrives in pulses, not randomly. The solar system has almost certainly received visitors from many different parent systems throughout its history. We simply had no way to identify them as such until we developed the instruments to find objects on hyperbolic orbits. The discovery of One-Eye Oumuamua in 2017 was the moment that changed. The 3 visitors since have given us the first real look at what is arriving. And what 3-Eye Atlas showed us, in particular, is that some of what arrives is extraordinarily old, material from the earliest chapters of the galaxy's history, carrying chemistry that predates the Sun by more than twice its current age. The molecular inventory of 3-Eye Atlas's coma included the building blocks of prebiotic chemistry, not life, not the suggestion of life, but the molecules that, under specific conditions of temperature, pressure, and radiation, participate in the reactions that can, eventually, produce amino acids and nucleobases. Interstellar objects carry these molecules across the galaxy as a routine consequence of their existence. Whether those molecules survive impact with a planetary surface, whether they contribute to the chemistry of any world they reach, whether the chain from interstellar delivery to biological complexity has ever closed anywhere, these remain open questions. 3-Eye Atlas does not resolve them. What it does show is that the precursors are present, and that the transport has been happening for as long as planetary systems have existed. Some of what this object contains was synthesized in a cold molecular cloud more than 10 billion years ago. Some of it crossed our sky in 2025. On the 16th of March, 2026, 3-Eye Atlas passed within 0.358 astronomical units of Jupiter and continued outbound. It is now past the orbit of Jupiter, heading towards Saturn's and beyond, fading with every week that passes as the solar heating that drove its extraordinary activity falls away. The sunward jet has weakened. The coma has contracted. The spin-up that pushed its rotation period from 16 hours to 7 has ceased to accelerate. Within months, the object will drop below the detection threshold of even the largest ground-based telescopes. Within years, it will cross the orbit of Neptune and disappear into the outer solar system. Within decades, it will pass the heliopause and re-enter the interstellar medium, carrying whatever portion of itself the sun's warmth did not strip away, continuing a journey that has no destination and no end. The data it left behind is still being read. The JUICE spacecraft downlinked its observational dataset on the 17th and 20th of February 2026. The isotope papers were submitted to Nature and Nature Astronomy in March 2026. The full spectral analysis of the Tenerife campaign is ongoing. The post-perihelion compositional evolution has not yet been fully characterized. This is how major discoveries work. The first wave of results establishes the framework, but the papers that ultimately matter most are often written years later, when the full dataset has been reduced and the implications have had time to settle. The picture of 3I Atlas that exists today is almost certainly incomplete. The most important thing it told us may not yet have been published. What we can say with confidence is this: before 3I Atlas, the ancient galaxy was something we studied through the light of old stars, indirectly, inferentially, through models built from spectroscopic observations of metal-poor stellar atmospheres and theoretical calculations of protoplanetary disk chemistry in low metallicity environments. After 3I Atlas, we have measurements, we have isotopic ratios, and directly obtained from physical material that condensed in an early galaxy protoplanetary disk, preserved intact through 10 billion years of interstellar travel, and read by a telescope in orbit around the Sun. Planet formation in the ancient galaxy was volatile rich, even in metal-poor conditions. The thick disk produced intact planetary systems with cold, deuterium-enriched, carbon dioxide-dominated compositions that are distinct from anything in our own solar system. Interstellar objects are not rare anomalies. They are the normal product of planet formation, arriving continuously, carrying galactic history in their ice. The deuterium ratios, the carbon-12 to carbon-13 ratios, and the nitrogen-14 to nitrogen-15 ratios. These numbers were written into the molecular structure of 3I Atlas at the moment of formation, when the disk was cold and dense and the ice was condensing for the first time. The universe was less than 4 billion years old at that moment. The Milky Way was still building its thick disk from the first generations of metal-poor stars. The Sun would not ignite for another 6 billion years. The fingerprint was set then, and it survived. Cosmic rays altered the surface over 10 billion years of exposure, but the bulk isotopic composition of the interior ice was untouched. When Martin Kordener and NX Roth measured those ratios in late 2025 and early 2026, and they were reading a record that had been waiting since before the solar system existed. The chain of events required to produce that reading is almost too long to hold in the mind at once. A cold molecular cloud collapsing, a disk forming and condensing molecules at temperatures below 30 Kelvin, a giant planet flinging this body into interstellar space, 10 billion years of travel through the dark, and a civilization that had just barely developed the instruments to understand what it was looking at. 3I Atlas left its parent system 10 billion years ago. That system is gone. Its star exhausted its nuclear fuel billions of years ago, expanded, shed its outer layers, and collapsed to a white dwarf or less, perhaps in the process destabilizing whatever planets had survived long enough to see it die. There is no telescope that can find those remains. There is no catalogue entry for that star. The system it belonged to existed in the early thick disk when the galaxy was young, when the stars forming around it were the first generation of stellar objects massive enough to die quickly and enrich the interstellar medium with heavy elements for the first time. Everything that system built is gone, except for this. The object we watched cross our sky for a few months in 2025, the object that lit up its coma at 6.4 astronomical units, that turned the instruments of every major space telescope in the world toward its fading light, that released its ancient chemistry to the infrared detectors of the James Webb Space Telescope before the Sun could finish stripping it away, was the only surviving piece of a world that no longer exists. We had a few months. We used every instrument we had. We read what the ice contained, and then it left.